But yeah, so today we're going to talk more about storage allocation. And in particular, we'll talk a bit about the lower levels of the stack underneath the allocators we talked about last time. And then we'll get into the issues and design choices that arise when we want to do storage allocation in a parallel context. But first, I want to make a couple of quick announcements. So the first is that I believe we've issued a clarification on one of the questions on the quiz. People can, one of the TAs can speak up and correct me if I'm wrong about that, but I think there was one question where there were actually a couple of plausible answers related to one of the task graph scheduling things.
Actually, there's only one correct answer, which was A,
okay.
And I just simply got it wrong. I'm not sure what came over me.
I actually thought it is possible. So I thought about this when we were authoring the quiz, and I think it may be possible for the compiler. It seems like it ought to be possible for the compiler to issue a single join point, or construct code that separates the top level. But anyway, yes. So we.
But in any case,
a bunch of people got points back for.
And then we didn't take off people who made the same mistake I did, as much as. But anyway, you can be confident that you know.
Yes, scores monotonically increased.
I wouldn't get an A on. I wouldn't get a perfect score anyway in 6172.
Yep. And then the other announcement is that we posted a poll on Piazza asking for your guys' thoughts and input on how we should handle election day. So we have our class is Tuesday, Thursday. Election week is the normal class schedule. So we have a regular lecture scheduled that day, which we will probably do, but you're all obviously welcome to watch it on your own time later, since we record them and post them all online, just like normal. But we have one deadline that week, which is a homework, also due that Tuesday, and we're considering whether and how we might reschedule that or give you guys extra leeway given the added pressure, the need for many of you to find time to actually go vote and all that kind of stuff. So election is in a little under 2 weeks, 2 weeks from last Tuesday. So if you have thoughts on how you'd most like to see that managed, please please answer the poll on Piazza. No comments on the political stance of the class at the moment in response to what's on Slack. But okay, so before we get all the way into parallel allocation, I first want to review a little bit more about how memory allocation works in general. So what are the primitives that we have at different levels of abstraction, and how do they work? So you're already familiar with the core heap allocation interface provided in C. So you have malloc and free, which you've all used in your programs by now. So with malloc, you request a block of memory of some arbitrary size S, and then the implementation, the heap allocator that's underneath malloc, is responsible for allocating and returning a pointer to a block of memory containing at least S bytes. Now, C being a weakly typed low-level language, the return type is just a void star, so it's a pointer to whatever you want to interpret it as. So it's usually good practice to immediately typecast it to whatever you actually intend to use if you want to have meaningful types in your program. But again, the interface here maps quite nicely onto what we had with our binned free list scheme. So the allocation, malloc is responsible for returning a pointer to a block that's at least as big as we asked for, but it's allowed to give us something bigger. And then with free, you can release a previously allocated block back to the heap. So you have to free a block by giving the pointer that the allocation gave you in the first place. So that's a pointer to the beginning of the block. You can't just free any arbitrary pointer anywhere in memory, like in the middle of a block somewhere. And the reason's pretty obvious if you think back to how our heap allocators work. So they were keeping track of list of fixed size fixed blocks, and so they're probably using some metadata being tracked about each of the pointers returned to understand what's free and for reuse and what's already been allocated. So there's a bunch of bugs that we saw that can come by misusing freeing in particular. So you can fail to free memory, and that gives you memory leaks. You can free things more than once, double freeing, and that's almost always a sign of a bug and will often lead to a seg fault or something. And then finally here, there's one more routine that you may not have seen, but that's a close cousin of malloc, and that's this routine memeline. So memeline is like malloc, but it takes an additional size argument A, which is an alignment factor. That alignment factor A has to be a power of 2, and then the effect is to allocate and return a pointer to a block of memory containing at least S bytes. So that's the same as we had with malloc, but now with the added guarantee that it's aligned to a multiple of A. So aligned allocation is useful because it can be good for performance. And actually, I'm curious if anybody has any thoughts about why this is good for performance. Anybody want to speak up or post on the Slack why we might want to do aligned allocation sometimes? Yeah, some instructions we've seen, like some of the vector load and store instructions, which multiple people are mentioning. Vector memory addresses often perform best when they're aligned. And actually on x86, there's separate instructions for aligned versus unaligned vector loads and stores. Somebody else raises the question of page faults. I'm curious if you can maybe expand on what you mean by that. I think maybe the idea is we want to align things to page size granularities so that we get an allocation that takes up one or a fixed number of pages or the minimum number of pages possible. And those are all good ideas. Sometimes it's also useful just to make sure that our structures don't span cache lines. So we want to keep, make sure that some related object in memory is always going to reside on one cache line instead of it being spread across 2. All right, so those are the core library routines for allocating and freeing memory at the user level in C. Question coming in, why don't we always use memeline? Is the downside wasted space? Yes, the big downside with memeline, I think it's potentially more expensive, but the big obvious downside is it's going to lead to a higher level of internal fragmentation. So our allocations are generally all going to be rounded up to some multiple of, say, cache line alignment or something like that, which is going to mean we're wasting that extra space. Sometimes that's worthwhile trade-off. Sometimes we'd rather have our data packed more densely in memory, so our memory footprint is smaller. Okay, so these are some of the core library routines we have for allocating and freeing memory at the user level in C. But now you might ask, we talked about implementing heap allocators, which is basically implementing the algorithms underneath these routines. But where did those routines themselves get the memory for their heaps in the first place? Does anybody have any ideas how, we talked about if we have a heap that has a bunch of pages in it already, allocated to the process, how we can dole out the blocks within it using our heap allocation scheme. But how would our implementation of malloc actually request memory for its heap? Does anybody have any thoughts? Yeah, some people are, exactly. People are talking about syscalls in general, mmap, sbreak, and that's exactly right. So under the covers, the implementations of our heaps are going to have to interact with the operating system to request that memory be allocated. So now let's drop down a level and talk about how we can explicitly interact with the operating system memory management for our process. So on Unix-like operating systems, the core interface to allocate memory to a user process is the mmap system call. And mmap works by controlling the virtual memory mapping for the current process. So there's lots of different things you can do with mmap, but the most basic is just to request the mapping of a new arbitrary sized region of virtual address space into the process. So what we're doing in this case, you see an example call to use mmap in this relatively simple way, is we're requesting size bytes of memory. We're saying we'd like our current process to have read and write access to that memory. And we want it mapped privately just into our current process and anonymously, so it's not named in a way that can be referenced by other things. Some other stuff related to advanced features of mmap. And then, when we make this call, the Linux kernel will find us a contiguous unused region in the address space. So in the whole 64-bit virtual address space our process is running in, it'll find and allocate a contiguous region that's large enough to hold size bytes. So it's at least as big as the size that we requested. Then it's going to modify the page table to map that with the requested permissions and everything into our process's address space. Create any necessary virtual memory management structures to track this within the OS, and basically set everything up so that that memory is now allocated and usable by our process. Now, you might have seen mmap in other contexts. You can also use mmap in all kinds of other ways to map the contents of files on disk into memory. That's what this argument is about. So you can interact with files rather than using like fread and fwrite. You can just say mmap the whole thing and then treat it as an array that's in memory. You can use mmap to play tricks where you alias multiple pages over top of each other. So you can map multiple virtual address ranges to the same physical address range. You can protect memory or make it so it's only read-only or only accessible by certain processes and not others. You can map shared memory between multiple processes and do all kinds of other powerful things. But this basic idea of just mapping a new region into our as readable and writable into our virtual address space is kind of the most core functionality of mmap. So we're just it's a way we can allocate more virtual memory for our process. And indeed, this is what allocators like any implementation of malloc are going to be using under the covers to allocate memory, the memory they need for their heaps. So when they need more memory to grow the heap, they'll call something like mmap to get it. Okay, so then how does mmap actually work under the covers? The most key thing to know is that mmap is lazy. So when we call mmap, we're not actually immediately allocating physical memory for the whole region we requested. Instead, we're just the operating system is just going to update the page table with entries making it valid to read or write in that region. So it's going to unprotect that region virtual addresses, but it's going to configure them in a way that they point to a special 0 page and mark that page as read only. And this is basically a trick that we get that we can use to zero initialize all that memory, have all that memory appear as 0 initially. Any reads to it, to the whole region, are all going to map to that special 0 page and return zeros. And then the first time we write to one of these pages, to any of these pages, it's going to trigger a page fault. And at that point, the OS is going to get woken up to service the page fault. It's going to recognize that what we're doing is trying to do our first write to something that we've mapped but not yet physically allocated, and then it's going to actually physically allocate a new, fresh physical page, modify the page table to point to it, and then restart the instruction. So we basically have copy on write 0 memory as the starting point for these allocations. And because of this laziness, you can actually mmap basically arbitrary amount of memory. Like you can mmap up to the virtual address range limit. So you can easily mmap terabytes of virtual memory on a machine with only say a gigabyte of physical DRAM. And that's because until we actually write something to all of these pages, they aren't going to be physically allocated. And they're only physically allocated one by one as we write to them. So a process, if we mmap it way more virtual memory than we have physical memory, that mmap is usually going to succeed. But if our process actually proceeds to try to use all of it, it might die much later when the OS exhausts resources trying to allocate the pages the first time they're being written to. All right. So mmap kind of sounds similar to malloc. It's it's also a scheme for an interface for requesting the allocation of memory in our process. So what's really the difference between malloc and mmap? So I mentioned before that the malloc and free functions, these are the user level interface, the C standard library user level code that handles allocation allocation and freeing of heap objects entirely in userland. Then that userland heap management code can use any of these available system facilities, things like mmap, to actually allocate the virtual address space needed to store pages of its heap from the kernel. So the heap management code within malloc is generally going to satisfy most requests from the heap storage that it already has sitting around. And it's only when that heap storage is exhausted or getting close to being exhausted that it's going to have to mmap more of it. So now a question that you should think about is, so I just described how malloc sits on top of mmap, but at some level, mmap is still a scheme that does roughly the same thing. We ask for size bytes of memory, and it's a function we can use to ask for size bytes of memory, and it'll give us a block that's at least that big. So why do we actually need both of these things? Why can't we just call mmap all the time? Does anybody have any ideas? Yeah, exactly. So two key issues that have been raised. mmap in general is quite slow. That's the biggest single reason. The cost of making a system call and updating, like just the raw overhead of making any system call, interacting with the security and privilege mechanisms in the operating system, doing a mode transition and all that kind of stuff, as well as all the overhead of actually having to update the page table data structures in the OS. mmap is really heavyweight. So you don't want to use mmap except on relatively big regions, whereas the heap allocators, as we saw, are designed to be able, they're often optimized for even very small sized allocations. So it's not totally unreasonable to use malloc even just for a few bytes at a time. And it would be really, really slow if you had to use mmap every time you needed a few more bytes for a new structure. And another issue is that, as Prem raises, often, I'm actually not sure whether this is required by the Unix interface specification, but in practice, what mmap's often going to wind up doing is giving you fresh pages, and virtual memory pages are relatively coarse granularity things. They're often, often at least 4 kilobytes in size. And so if 4 kilobytes was the smallest object we could allocate, we could do many, many fewer allocations before we were wasting all of our memory than allocating things down to individual bytes or cache lines, which are like 64 bytes. Okay. So now, since mmap is about changing the virtual memory mapping, I want to take a really quick digression to talk a little bit more about virtual memory. So this is just a quick review of material you might have seen in like 6004 or an operating systems class potentially. But the basic idea with virtual memory, to review, is that we're adding a level of indirection between the addresses that our software works with, all the way down to the actual load and store instructions in our processor, an indirection between those addresses and the physical addresses of data in our DRAM. And conceptually it looks something like this. So every address in our program uses a virtual address, and those are the 64-bit pointers that we load and store in all of our code. And then the system breaks down and thinks of each virtual address actually as 2 parts. The high order bits are what we call the virtual page number, and the low order bits are just an offset within that page. So virtual memory is made up of a bunch of fixed size pages. Like I said, the default for a very long time on lots of systems has been 4 kilobytes. Modern systems also support, they support a few different sizes. So your default page sizes are 4 kilobytes, and you can also have super pages of 2 or 4 megabytes, or some architectures support also like gigabyte kind of scale pages. but everything's allocated from a few of these fixed size chunks. So the virtual page number is all the bits needed to index into a chunk of, say, 4 kilobytes, and the offset is the remaining low order bits that index within that 4 kilobyte page. And the way a virtual address is interpreted is we first map that virtual page to a corresponding physical page or frame, and then the complete physical address is the same offset, but within the corresponding physical frame or physical page. So logically, our page table is a mapping of virtual page indices to physical page or physical frame indices. And we map from a virtual to physical address by taking the virtual page number, looking it up in our page table. That gives us a physical page number. We concatenate the same offset bits onto the end of it. The physical page number gives us which page or frame in physical memory we have, and the offset gives us where in that page the byte that we're referring to is looking. All right. So that's the basic idea of virtual memory. Like, all things in computer science, the secrets to building powerful systems with virtual memory is the basis for how we get lots of protection and security schemes, how we get memory protection and isolation between processes. So when one process segfaults and crashes, it doesn't bring down the whole system or corrupt other processes. So it's a really, really powerful technique. And the key is, the secret to all computer science, adding an extra level of indirection. But the whole thing relies on looking up through our page table. So remapping every virtual page to a physical page using our page table. So what happens if we don't have a mapping already in the page table? Or equivalently, if the corresponding page, maybe we have a mapping for it, but that mapping doesn't point somewhere in physical memory, so we don't have a corresponding page in physical memory, but it's mapped to that special zero memory as read-only, or it's mapped to somewhere on disk, but not in memory. What happens when we get a situation like that is it triggers a page fault. And a page fault is like an interrupt that gets serviced by the OS. So when a page fault like this happens, the OS is going to see if the process it's going to access some of its own data structures, which you can think of logically as the page table, but often augmented with a bunch of additional OS-specific metadata. So it's going to see if the process has permission to access that virtual memory range. If so, it's going to put a mapping into the page table. It's going to somehow allocate a page of physical memory and put a mapping to it in the page table. And if not, you'll get a segfault. And that's actually literally what segfault means. Segmentation fault refers to segmentation was an older name for simplified schemes for virtual memory and refers to an error in trying to translate from a virtual address range to a physical address range because that virtual address is not mappable by the process. So a key thing to note here, I've just referred to, I've said every load and store we're performing works with virtual addresses. So at the level of individual instructions in our processor, we're working with virtual addresses, but every single one of those has to map through the page table to translate into a physical address to know where it's actually going to be looking in DRAM. And you might imagine doing this in general through a whole big page table managed by our OS is really expensive. So actually walking through these page table data structures to compute that translation may take thousands of cycles to complete. And so the last key piece to know of how virtual memory, how to kind of think about how virtual memory is implemented that really matters from a performance perspective is something I alluded to in the last lecture and that we've talked about a couple of times but never fully unpacked. And that's how processors actually accelerate this address translation process. And that's using a translation look-aside buffer, or a TLB. So you remember every single load and store instruction is working with virtual addresses here. So even down inside our processor pipeline, we're still working with virtual addresses. And the processor needs to be able to translate these to physical addresses really quickly to be able to actually execute any instructions with them. So translation look-aside buffer is kind of a weird mouthful of a name, but really you can just think of it, I think a better, more descriptive name for it is a virtual address translation cache. So it just caches recent translations from virtual to physical page numbers in the hardware inside the processor, so that we don't need to actually look up in the full page table for every instruction. So TLB lookup is really fast. So that's the much faster than actually traversing some data structure out in memory, storing a page table. But natural question now is why you might expect it to see something it's already seen. And basically the answer here, like with lots of other uses of caching, is a combination of spatial and temporal locality. So if our data, if we're often working with compact data structures that are all lying on the same page, we're going to have a whole bunch of loads and stores for different parts of those data structures or different parts of those arrays that are all going to be going through the same virtual page to physical page mapping. Because remember, these pages are the granularity of something like 4 kilobytes. So every access within that 4 kilobyte bound is going to correspond to a single translation, so a single entry in our TLB. And you also, in general, in programs, expect some amount of temporal locality. So you expect to reuse, load and store the same addresses multiple times, potentially close together in time. And obviously, if we're accessing the exact same address, it's going to also be the same entry in the TLB. So because of stuff like this, we sometimes refer to TLB effects as being a potential performance pitfall of different kinds of code. And you can write a program that misses the TLB all the time. And the way you do that is by having scattered accesses all over the virtual memory space. So, but so if every access is spread apart by at least a page size, and I never touch the same thing twice, so I'm striding through memory by a stride of at least 4 kilobytes, every single request is going to trigger a page fault and a TLB miss, and that can get really expensive. But in general, if you access memory close together or in a linear order, then you're not going to get very many TLB misses. And you'll also benefit from things like prefetching that also help to make the memory system efficient. All right, that's it for our quick tour of how virtual memory works underneath our allocators. Any questions on this, on what we've talked about so far? Looks like no for now. Okay. So now let's get back to our allocation schemes and see how they change in a parallel context. And just like last time, let's start with stacks. So if you remember last time, we had basic stacks, which we can just implement using an array and a pointer. In parallel, we wind up with needing to use a somewhat more complicated data structure, what are sometimes called cactus stacks. So in the serial setting, as we saw last time, stacks are really, really simple. So it's just an array and a pointer, and you push and pop just by moving that pointer. And we saw how the C compiler can easily use a stack to automatically manage local memory for function calls and returns. So in serial code, the execution you can think of as just a serial walk over the function call tree. So if we have a program that makes a series of calls like this, in this case, first we're in this function A, then A calls B, and the state of the stack we can see progressing through these calls over here on the right. So we start out in A, we have some piece of stack for the local variables in the function frame for A, that's here. A calls B, which pushes more space onto the stack for B to use. B returns back to A, which pops the frame for B off the stack. A can then call C, which pushes a frame for C onto the stack. C calls D, pushes another frame, pops that, calls E, pushes a frame for E. And if we think about what this means, this is the state of the call stack over time in this process. But the layout of memory is basically just this vertical axis. So this is horizontally, we're progressing through time, and vertically we have contiguous addresses in memory. So if you look at this, you'll notice, we always have the same frame in the same part of memory for A, because we're always inside the scope for A. But if you look, C, D, and E all occupy a bunch of the same region of memory that was previously, that was occupied earlier in the same program by B. So there's some aliasing or reuse of memory. And that's, the whole premise of our storage allocation schemes is we want to be able to allocate memory, then free it, and then reuse it for something else. And when we're following a stack discipline like this, we wind up with subsequent sequential calls from the same level of the stack, using the same level, the same lower further levels of the stack. Now, with stack managed memory in C, like the usual semantics for the C language, the rule is that a parent function is allowed to pass pointers to its stack variables down to its children. So A can pass a pointer to the contents of its stack down to B or C, or similarly from C down to D or E, but not the other way around. And you could sort of see why if you just look at the layout of the stack memory here. So, and if we returned a pointer from B's stack frame back to A, then we would have just popped or freed the memory that pointer is living in by the time we get back to some part of A. Maybe we then pass it further down to C. C's stack frame is potentially overlapping with where that pointer in B's stack frame was pointing. So if you pass a pointer from the child to the parent, you basically have a pointer to garbage by the time it goes back to the parent. And so you might get a seg fault, or even worse, you might just get some undefined, unpredictable behavior where you're clobbering some other memory. You don't realize that two different pointers are aliasing to the same thing, which can be really dangerous. So if you want to pass memory from the child back to the parent, where do you allocate it? And usually we have to allocate it on the heap. And this is one reason that sometimes functions in C require you to pass in the memory where you want the result to be stored as a function argument. And it's so the child doesn't have to do an expensive malloc, and the parent can decide whether to make space on the stack or allocate memory on the heap. So you are still making the parent responsible for allocating the memory for managing where it wants results from its children to be stored. Okay, so the core memory model of C requires that parents be allowed to pass pointers down to children. And in serial code, this is really easily implemented with just a plain stack. If you think about our serial execution for these functions, it's always fine for A to be passing pointers down to B or C. It's fine for C to be passing pointers down to D or E, because these pieces of memory are always still allocated and in scope when the child functions are running. But the next question we need to ask is, what happens when we want to spawn multiple child functions in parallel like we do in Silk? So in that case, say B and C are run in parallel. So we spawn B and then call C, for example. So with the serial stack, remember, we're reusing memory for B and C. So that's fine if you're running sequentially, but obviously it won't work if the two are running at the same time. You can't store multiple things, the stack frame for C and the stack frame for B in the same piece of memory in the same place at the same time. And this is where cactus stacks come in. So the big idea with a cactus stack is that it supports multiple views, multiple local stack-like views from different spawned functions in parallel. So in this case, B, D, and E, say, might all have been spawned and be executing in parallel. And they can each see their own view of the stack. So the whole core promise of Silk is that as long as we write race-free programs, we get sequential semantics. So the program without spawns and without parallel execution has the same semantics as with them. So we know that regardless of how we spawn things in parallel here, assuming that we're not introducing any races, and certainly if you're interacting with the stack variables, regardless of which of these edges switch from plain function calls, plain sequential function calls to spawns, the semantics should be the same. And that means that at any time while B is running, it should locally see a stack that looks like this. When C is running, it should locally see a stack that looks like this. D should see a stack that looks like this, and E1 that looks like this. And the Silk runtime system supports a cactus stack abstraction to make it easy for programming. It means that you can obey the same rules about function local memory and caller-callee relationships as for programming in plain sequential C and C++. So you can pass a pointer from a parent to a child, whether it's a sequential regular function call or a parallel spawned function call. And the behavior should be the same. And in order to be efficient, there shouldn't be any copying for A. So they should all see actually, in order to be efficient and also in order to be correct, because this memory is shared. And if somebody mutates a pointer into A stack, it should be visible to everybody. So the shared frames should all be living and pointing to the same place in virtual memory. So we obviously can't do that with just a single linear stack. And it turns out that the simplest way to implement a cactus stack is just to allocate all these frames on the heap. And then store a pointer to memory, to the frame memory on the heap instead of on the stack. So the idea with a simple heap-based cactus stack, so this is kind of the default or historical implementation for this abstraction, is that you just allocate each spawned function's frame on the heap. So when you do a push, so you call a new function or spawn a function and push a frame for it onto the heap. When you do that, instead of just incrementing a single stack pointer, you do a heap memory allocation. So you basically call malloc for the size of that frame. And then when you pop, you do a free. So each of these frames now, because they're not just all living contiguously in the stack memory, each of these frames has to store an explicit pointer to its parent frames. Since they're not contiguous, you can't just pop by subtracting again. You have to explicitly look up the parent frame address. But by basically modifying the C compiler and what its calling conventions are, you can implement the same C semantics in this way using heap allocations for each function stack frame. So lots of early systems, like the original MIT Silk, used heap-based cactus stacks like this. Does anybody have any ideas? So this is this works well as long as all the code you're writing is Silk. But does anybody have any ideas about what problems this might raise? Allocating all these stack frames off the heap. Yeah, one observation is this is probably slower when not running in parallel. Anything else? A few people are working on ideas. Interfere with variable allocations. What do you mean by interfere with variable allocations? You can feel free to speak up on Zoom if you want to expand on that, Shengtong.
Like maybe the stack will be like interleaved with like variables, like memory for variables.
You mean like interleaved with other things on the heap, like things that the user allocates using malloc, that kind of thing?
Yeah.
Yeah, so that would likely be the case. I think it's still safe from the standpoint of kind of the semantics of the C language, because you're not supposed to read outside of your allocations. So you shouldn't, read outside of read or write outside your stack frame, or write outside of what malloc gives you. So the fact that those things are next to each other in memory shouldn't be a big deal, but it might have performance implications. But it turns out there's actually a bigger practical issue. A couple people seem to be guessing. Yeah, good question is what happens if the stack frame size needs to change, like a variable sized array on the stack. And yeah, a lot of this seems to also relates to the performance implications. So implementing dynamic alloca in this context is potentially a little bit more complicated. But the big issue is actually with legacy code. So especially when you have precompiled binaries. So remember the way the stack is normally implemented in C. It's actually just a convention that the compiler maintains for how to push and pop on the, what push and pop on the stack mean in terms of the underlying implementation of the generated code. And in a traditional C compiler, and with what we call that interface of how function calling works and how memory is managed across function call boundaries is often it's specified by what's called a calling convention, which is an assembly level standard for how a function call should be implemented. So the calling convention for a traditional C compiler basically depends on this idea of a linear stack, a single linear stack. So when we're just using the Silk compiler, it can choose to implement every stack frame and every stack frame push and pop using new heap allocations. It's possible to implement the semantics, the high-level semantics of C using a different calling convention that works with heap allocated stack frames. But if we want to be able to link Silk compiled code to a library compiled with a different compiler that assumes a different calling convention, then that's potentially not safe. So it's hard to interoperate between code that uses a calling convention on an actual linear stack, while the other uses a heap-based cactus stack. So this heap-based scheme is what was used in the original Silk, but is not used in the current cheetah-based implementations that we use today. So I think this might come up a little bit later, but I believe they use a bunch of separate linear stacks and potentially clever virtual memory mapping for sharing data between them. All right. So now let's think about how much memory this type of stack management will use. So thinking about this simple heap-based cactus stack scheme. So it turns out I'm going to claim that if S1 is the stack space required by a serial execution of our Silk program, then the stack space required by a P worker parallel execution using a heap-based cactus stack like I just described is going to be bounded to be at most P times S1. So we need at most P times as much memory for a P processor parallel execution as we did for serial execution. And this is a really nice property to have. And it turns out to be maintained just because of the way Silk's work stealing runtime scheduler works. So a consequence of that algorithm and the whole work first principle is what we call the busy leaves property. And that's that every active leaf frame in the call stack or in the cactus stack actually currently has a worker executing it. And this is important because you don't want to have a runtime system that explodes memory. So it's perfectly possible to have a scheduling scheme that spawns numerous different functions, allocates all their stack frames before bothering to get around to running any of them. But we really don't want to use 1,000 times more space just to get a few processors busy. But a key characteristic of Silk's work stealing scheduling algorithm is that you'll never have a leaf that nobody is working on. And it's just because of the fundamental nature of the algorithm. So this is another kind of nice optimality property that it has. All right, so any questions on what we've seen so far? Okay. So now let's think for a little bit about the behavior of a related problem that we've seen before. And that's our divide and conquer algorithm for parallel matrix multiplication. So if you remember this from earlier in the semester, you don't have to remember it in detail, but the code looks like this. So the basic structure, this is our matrix multiply, divide and conquer algorithm. We're multiplying A and B and accumulating it into C. We have some base case, but the default, parallel divide and conquer behavior is that we're going to allocate a new array for the result. We're going to spawn 8 subproblems as children. Then we're going to sync, and we're going to add all the results together accumulate all the results. So the key thing with regard to memory is how we allocated free during this parallel recursive decomposition. In this case, we're using heap memory with malloc and free, but we're still following a strict stack discipline. So you notice that we start at the start of the function, we allocate the memory that we're going to use internally, and then we free the memory right before we return. So even though we're calling malloc and free to allocate this on the heap, it's basically following a stack discipline as we recurse through the functions. And our parallel stack space bound that we just saw for the cactus stack case holds even if we're doing malloc explicitly. So as long as we're allocating and deallocating according to a stack discipline, this same bound we saw here still applies. Okay, so now let's think a little bit about this algorithm and how it's going to behave. So the first question we want to ask in line with what we've done in the past is, what's the work? Does anybody have any thoughts? What's the work we're doing here? N squared log n, not quite. Yeah, n cubed. So this is a matrix multiply. In general, for n by n matrix multiply, you're always doing at least n cubed work. But this is a work efficient algorithm, so we're doing exactly n cubed work. Okay. So then what's the span? What do people think? We're always working out these 8 children on subproblems that are n by n over 2. But importantly, we also always have this add at the end. Yeah, great. Log squared n. It turns out that the span of add is going to be a doubly nested loop over the 2 dimensions of our matrix. If we do that in parallel, the span is going to be theta of log n, or the theta of log n, and then the theta log n's between our top level parallel recursion and the add combined to give us log squared n. Okay, so now how should we think about the space? So this is, we haven't done space allocation before, but the analysis is going to look a lot like the recurrence relations for divide and conquer algorithms, for work and span and divide and conquer algorithms that we've seen before. So the space that we allocate at each step is going to be a recurrence on n over 2 plus an n squared matrix for the result. And it turns out, I'm actually going to skip over this for time, not make you go through, not go through your master method cards, but it turns out that gives us theta n squared space. So thinking back to the bound in general that we were talking about on heap-based cactus stacks, assuming that we're using a SilkWorks dealing scheduler, which ensures the busy leaves property, does anybody want to guess what that means? Our overall bound. So this is the space in the sequential case on one processor. What is the bound given that on how much memory we need on P processors? If you think back, we're here. Yeah, great. So we just have this factor of this extra factor of P. That was what the basic space bound on a cactus stack told us. With as long as our scheduler enforces the busy leaves property, we have at most P times the amount of memory we need in the sequential case. Okay, great. So it turns out that in this specific case, we can actually prove a stronger bound. And I'm probably going to skim over this pretty quickly for time, but you can follow in more detail on your own. And the basic idea is that most of the space is being allocated near the root. So we have this branching factor of 8. And the worst case is going to happen if we branch as much as possible at the top. So we're allocating allocating as much as possible towards the top of the call tree, and then go serially down from there once we've expanded out to p nodes. So we're going to, this worst case is going to come when we branch fully 8-way down to a level k with p nodes, and then branch serially from then on. So the level k at which we have p nodes that can run in parallel with a branching factor of 8 is going to be when 8 to the k is equal to p. So that implies the level of the tree at which we have p parallel tasks is going to be log base 8 of p, which is equal to log base 2 of p over 3. And then that winds up, if you plug it all the way through, giving you a slightly tighter bound than we had in the general case of theta p to the 1/3 n squared instead of p n squared. All right. So I want to take a quick breather for a second and then come back and talk more about parallel heap allocation. So I'll be back in just 1 minute. All right. Sorry, it feels like summer, so I had to turn on my air conditioning. Okay, so now let's dig back into storage allocators in general. So this is, performance engineering. So the first thing we care about is obviously going to be our allocator speed. Now, what might that actually mean? How can we define the speed of our allocator a little more concretely? Well, I think often the most useful thing to think about is the speed of an allocator is the number of allocations and deallocations per second, or the rate at which our allocator can sustain allocations and deallocations. Now, questions we're thinking about is, obviously the speed is going to be affected by the size of the allocations that we're trying to perform. You might expect that it in general is going to cost a little bit more to allocate at least a little bit more to allocate large blocks than it is to allocate small blocks, at least when we consider constant factors. But a worthwhile question to ask yourself when thinking about how we should optimize the design of allocators is it more important to optimize our allocator speed for large blocks or small blocks? Does anybody have any thoughts on this? Small blocks. Yeah. Why? Good guesses. I'm curious if people want to expand a little bit more. So maybe in general we have more small blocks. Yeah. So yes. So everybody seems to be hitting on the idea that small blocks are allocating and freeing of small blocks is just going to be more frequent, and that may well be the case. I think that often is the case, but it turns out that there's an additional kind of reason that drives that, and reason why overhead in larger blocks often isn't as big a deal, which is that usually when we malloc something, we're going to touch it. So if we allocate a big block, we're probably going to actually wind up touching all the bytes in it at least once. And if we allocate a small block, we're only going to be touching, necessarily going to be touching a smaller number of bytes. So a large block takes a long time to actually populate. And so the allocator time often has relatively little effect on the overall runtime relative to that. So, if we're going to malloc megabytes of space and memcopy something into it, that memcopy is going to take a lot longer than grabbing a chunk of a few megabytes from one of our big heaps. Whereas if we're only allocating a single byte of memory from a very small heap, and then writing that 1 byte. Writing 1 byte takes 1 instruction. Writing even a few bytes takes only 1 instruction. So often we have a lot less useful work that's amortizing the overhead of these allocations. Okay, so that's speed. Now the next thing we care about, which we touched on a little bit last time, is fragmentation, or more generally, the storage overhead of the allocator. And we can define total fragmentation generally like this. So first we're gonna say the user footprint is the maximum over time of the number of bytes in use by the user program. So those are things, the maximum over time of the number of bytes that the user has requested be allocated. We'll call that M. And then the allocator footprint is the maximum over time of the number of bytes of memory that the allocator is holding on to. So the number of bytes of memory that's been provided to the allocator by the operating system. And we'll call that H. And then in general, we can think about the total fragmentation as just a ratio H over M. So if we've allocated way more space to the process for the heap to use, then we're actually using at any given time for useful user allocated data, then we have, we call that high fragmentation. And then conversely, we can think about the space utilization as the fraction of memory allocated to the heap that's actually being used by the user process. And importantly, these are the peak usage, not the total that's being allocated. So this is the peak at any given point in time. One thing to note is that H, or the amount of memory that our allocator needs to store its heaps, for many allocators tends to grow monotonically over time. So if you look at, even if you don't have a memory leak in your process, if you look at the size of allocated virtual memory for that process, you won't see it go down very much. It'll usually only increase. And that's because many allocators don't tend to return memory back to the OS, even when the user frees most of everything. There's a variety of low-level reasons for that. There is an munmap command that's a corollary to mmap that can return memory. But it turns out that most OSs don't actually have a very good implementation of this. The cost can be very expensive. It can even be super linear if you do it a lot. It tends to be very heavyweight. There's a faster scheme called madvise, which I'll mention in the fast allocator if we have time at the end, which just says, I'm not using this physical page, so leave it in my memory allocation, but it currently contains no useful data. So the OS is free to deallocate the physical pages that mapped it, and it doesn't have to save them to disk when it does so. So that's a scheme that some fast allocators use to try to get memory back, but the virtual memory allocation is still only growing monotonically. A theorem that we saw last time is that the fragmentation for a binned free list scheme, the internal fragmentation is bounded by big O of log M, assuming we're using power of 2 scheme for our bin sizes. And then another comment, something that's useful to keep in mind is that while we're working with 64-bit processors, so our virtual addresses are 64 bits, the virtual memory implementations, things like the TLB and all of that infrastructure on most of the machines we see today, so pretty much any x86 64 machine you're likely to be running on, has 2 to the 48 bytes, so 48 bits of usable virtual address space. And then an order of magnitude, a really big server might have something like 2 to the 40 bytes, or about a terabyte of actual physical memory. Okay, so now let's quickly nail down a little bit more terminology. So first is space overhead. So that's the space used by the allocator for bookkeeping. So this is aside from fragmentation and stuff. You might imagine that our allocator is going to need some of its own data structures to actually track what's going on, track what's been allocated and deallocated. Maybe there's some bitmaps somewhere, other things like that. Those are space overhead for the allocator. Next is internal fragmentation. We saw that last time, and that's the waste due to allocating larger blocks than what the user actually requests. So our binned free lists, for example, always rounded up to the nearest bin size that was larger than the request was. You can use other sequences besides powers of 2. So you could use Fibonacci to reduce the internal fragmentation from at most 2n factor to, I think you get a golden ratio factor in that case, but the basic idea would be the same. Then last time we also saw external fragmentation, and that was the waste due to the inability to use storage because it's not contiguous. So this is waste outside of our, in between the chunks that we've allocated. These are unused blocks within our heap segments. So for example, if I allocate a whole bunch of 1-byte things, then I free every other one, and now I want a 2-byte chunk, I'm not going to be able to find it from any of that space that I just freed, because I just have a bunch of discontiguous 1-byte chunks. And finally, one more new term is blow up. Or blow up is maybe used in multiple contexts, maybe more accurate here would be parallel blow up. And so for a parallel allocator, we talk about blow up as the additional space required beyond what a serial allocator would require. Okay, now we're ready to dive into kind of the climax of it all. So we saw that we can, for example, reduce allocating off the stack in parallel with cactus stacks to allocating off the heap, but we haven't yet seen how we do heap allocation in parallel. This is the most general allocation scheme we talked about last time. How do we generalize something like a binned free list to work in a parallel setting? So the first strategy we can use is really simple. It's just to use a single global heap. And this is actually what you'll often get by default with the C runtime malloc in most C implementations. So if you just call regular malloc on Linux, it's probably going to work like this. And the idea is that all threads and all processors are just going to share a single global heap. And then anytime they want to allocate or free anything, those requests and the interactions with the heap data structure are going to be mediated by some kind of global synchronization. So we're either going to have a lock, like a mutex, that says, that controls our ability to manipulate the heap data structures, or maybe we'll use some clever lock-free data structures, but to preserve atomicity. But in general, we're going to have a whole bunch of threads running on a whole bunch of processors, all trying to interact with the same shared heap data structures. So the first question we can ask here is, what's the blow up with this? Remember, blow up is the overhead above a serial allocator. In this case, conveniently, it is a serial allocator. This is literally just our regular serial heap scheme, but with a lock in front of it so that people have to access it in a serial fashion. So the blow up is just 1. So that's great. But does anybody have thoughts on what the problem with this strategy is going to be? Maybe you want to guess? Yeah, exactly. So we're going to have a lot of overhead due to synchronization because everybody's going to be bottlenecked on the lock. And the key issue is what we call contention. That's going to limit our scalability. So if a bunch of people are trying to interact with the heap at the same time, so you have a bunch of calls on separate threads to malloc and or free, they're all going to need to touch the same data structure, so they're all going to be racing to hold the same lock. And while any one of them is holding it, the others won't be able to. So this brings us to another concept that we care a lot about in parallel systems in general, and that's scalability. So ideally, we'd like it to be the case that as the number of threads or processors grows, the time to do whatever we're interested in doing, in this case, perform an allocation or a deallocation, shouldn't increase, or at least shouldn't increase too much. And the most common reason why you might not have good scalability is lock contention, or in general, contention on synchronization data structures, like in that case. So now I want to ask a question kind of related to something we saw a little while ago, which is, do you think this kind of lock contention for a global shared heap allocator, is this going to be more of a problem for large blocks or small blocks? Good guess. Small blocks, same as before. Yeah, indeed. Once again, the answer is the same as we saw with where we want to optimize allocations in general. And now, now we'd like to ask why again. And the reason is kind of similar. If a user program is always going to be writing all of the blocks, all of the data in any block that it gets back, the amount of time it's going to spend doing that for a large block is much bigger than for a small block. And if you think about what that means for lock contention, it's going to be spending more time, if a program's, say, in a loop between allocating a block and working on or populating that block and then allocating the next block and so on, or freeing it, and all the threads are doing that at once, the more time they're spending working on the block, the less time they're spending contending with the malloc synchronization structures. Okay, so the scalability due to the global heap lock contention is a big problem, in particular for small allocations, or when we have lots of threads. So how can we reduce this kind of contention and improve scalability? So the problem before was that we had to synchronize all the accesses to a single shared global heap. So the obvious alternative, in some sense, the other extreme of the design space, is we just have local heaps for each thread. So before we had one big shared heap, and all the threads interacted with it mediated by a lock. The other extreme is we just give every thread its own heap. So each thread, when you call malloc or free in that thread, it's going to manipulate only its own thread local heap. If we do that, we don't need any locking. So that's great. It's really fast. There's no synchronization between the threads needed. But the problem we run into in this case is what we call memory drift. And this can wind up causing blow up in pathological cases. And it can actually cause unbounded blow up in a pathological case. We'll unpack in a second. And the idea with memory drift is, think for a second about what happens if I call malloc of a block on one thread, and I pass a pointer to that block or pass ownership of it to a different thread, and then that thread is responsible for freeing it. What we've said here is that each thread does all allocations and frees on its own heap. So it's going to malloc pulling from its own heap, and if it has a pointer that it wants to free, it's going to put it back in its own heap. So if we have migration of data structure from one thread to another, so it's malloced, say on thread 1, passed to thread 2, which then frees it, it's going to be coming out of the heap for thread 1 and then getting put back into the heap for thread 2. That's what we mean by memory drift. The ownership over that block of memory is going to be drifting from one thread's heap to another one. And if we think about a pathological case for that, in the worst case, imagine that all the allocations in a program are happening on one thread and all the frees are happening on other threads. So then you're just, even if your program is only ever working with one object at a time, so you malloc it, pass it to another thread and free it, so that the maximum number of usefully allocated things is at most one block in this extreme case. You're constantly going to be having to make more heap memory for the thread that's doing the mallocs because it's never freeing anything and putting them back. So you're constantly going to be having to nmap more and more space for that thread. And then the free space in the heaps of the other threads where the frees are happening are going to be growing unboundedly. So they're going to be full of unused memory, but that's never going to be getting reclaimed because you're not calling malloc on those threads. So you can have unbounded blow up in this case. It's almost like a memory leak in a sense, if the allocator isn't smart enough to reuse things across heaps or put things back. And okay, so that now brings us to our third strategy. Good point. Memory drift is always on quiz 2, so worth committing that to your long-term memory. That now brings us to the third strategy that we can think about. The kind of in these basic schemes, there's a way we can kind of balance between these extremes, and that's what we might call local ownership. So the idea here is that we're going to say each object is labeled with its owner or labeled with the heap that it came from. So we're still going to do malloc the exact same way we did in a thread local fashion from our thread's local heap. So So that's going to be fast. It doesn't require any synchronization just like before. But with each of those objects, we're going to keep additional information that lets us know which heap it was allocated from, or which thread owned it. And then when we free, we're going to give it back to that thread's heap. We're somehow going to synchronize in order to do that. This is great in the simple case because allocating and freeing local objects within a given thread is still just as fast as in the pure local case. But the disadvantage is that freeing remotely allocated objects does require some synchronization. The good thing is it bounds our blowup to being at most P for P processors, which is not so bad. And then it has a nice property that we haven't talked about much yet, which is that it's resilient to false sharing. So if we had time, I would ask if anyone remembers what false sharing is, but it's actually a bit of a trick question because we haven't really talked about it so far. So what is false sharing? So this is related to the behavior of caches and cache coherence in a multiprocessor or multi-core setting. So in a multi-core setting, true sharing refers to sharing the same memory location. So if multiple processors are reading and writing the same memory location, then they're sharing that memory location. We call that true sharing because they're trying to actually touch the same piece of memory. False sharing is when they're interacting with different memory locations from each other, but that happen to be on the same cache line. And we'll see what that causes right now. So let's just look at a really simple example. So I have my idealized multiprocessor, and I have my processors down here. Each of them has a cache connected to a big shared memory bus and a shared DRAM memory. Then let's say the compiler, or maybe the interaction of the code, the compiler and the memory allocator happens to put variables X and Y in the same line of the cache, the same cache block. Now let's say this processor here writes to X. That's going to cause it to load that line into its cache and perform the write. And so now this processor has a modified copy of the cache line. And if you remember back into the sands of time, and we talked a little bit about cache coherence protocols, if this processor has a modified copy, anybody else reading has to first evict from this cache or read from this cache in order to be able to see it. So now let's say this other processor writes to Y. In order to implement that, we need to actually read and copy that cache block over to the other processor's cache. It has to claim exclusive ownership over it. So it's now been invalidated over here. It can perform the write. And now that this cache block is living exclusively on this processor. Now let's say first processor wants to write to X again. You have to do the same thing in reverse. So we're swapping that cache block back and forth between these processors as they alternate between writing things. But the key to this being false sharing is that they're actually not writing the same piece of memory. They're just writing two adjacent pieces of memory that happen to be on the same cache line. And if you imagine a program where I have two things thinking that they're hammering on local variables that they have exclusive ownership of, but under the covers, those are on a shared cache line and it's having to fly back and forth through the system, it's going to make all our memory accesses a lot slower and can lead to really pathologically bad behavior. Okay, so quickly, how does this kind of thing occur? And how can you prevent it in your program? So a program can cause false sharing by having different threads process nearby objects. As a programmer, you can sometimes mitigate this. False sharing is also always on quiz 2. As a programmer, you can sometimes mitigate this by using something like memoline, so aligning your objects on cache line boundaries and padding them out to be sure that they have an exclusive cache line all to themselves. But that's obviously sometimes wasteful of space. And an allocator, regardless of what your program's trying to do, an allocator can induce false sharing in a couple of different ways. So first, the allocator could, so when we have a single global heap for making multiple small allocations, there's no reason that those wouldn't necessarily give different threads small allocations coming from the same cache block. Or similarly, it can kind of happen passively if an allocation, pieces of an allocation or neighboring allocations that are on the same cache line get passed around by threads in the program to different cores. Okay, so let's wrap up by just quickly returning to parallel heap allocators. And the last thing we want to talk about are some advanced parallel heap allocators that deal with issues like this. So the big one that we're going to cover to wrap up now is the horde allocator. And we have a reading on this, which you should be sure to check out. And the idea with horde is to kind of combine the notion of local ownership thread local heaps, so the kind of strategy 3 we talked about a second ago, with a shared global heap. So we're going to have P separate local heaps, one on each processor, and one global heap. And we're going to organize memory into large super blocks, large pages or chunks of some non-trivial size S. These often might be virtual memory pages or even big disk pages or something. And then we're only going to migrate super blocks. We're only going to migrate memory between the local and global heaps at super block granularity. So whole super blocks may pass ownership between local heaps and the global heap. And the basic idea is, when the super blocks in a local heap get too empty, we're going to move it to the global heap. And if a local heap needs more memory, it can fetch it from the global heap. All right, so this is fast. It's quite scalable because almost all of the interaction with the allocator is done on separate thread local data structures. It still has bounded blowup, though, unlike any of the scalable things we saw before. And it also has nice resilience to false sharing. So legacy pun here, heap hooray, we solved the problem. So let's look really quickly at a bit about how horde works. So first, for allocation, let's just assume for a second that we're just working with blocks of a fixed size. Remember from our free list discussion last time, and then how we layered binned free lists on top of that, we saw how we don't actually lose any generality by doing this. If we have a fixed size heap allocator, we know how to build an arbitrary sized heap allocator with log n fixed size heaps. So say we're on thread I, then our implementation of malloc of a given size is going to be a simple algorithm that you see here sketched. So we're going to say if there's a free object in the local heap on our thread, then we're going to allocate from the fullest non-full superblock in our local heap. So we track all of the memory in our heap in terms of these superblocks, and we're going to pull an object out of the one of those that's most full that still has space. And that's going to tend to keep these things compacted also, as we talked about a little bit last time. Otherwise, if we don't have space in our local heap, we're going to go check the global heap. If the global heap is empty, we need to allocate a new superblock from the OS. We need to call mmap. Otherwise, if there is a usable superblock in the global heap's not empty, we pass ownership of that superblock from the global heap to thread I, and then we allocate the object out of that superblock. Okay. So the key idea in horde is that we're going to also return superblocks to the global heap when their utilization is low, so that other threads can potentially use it. And that's the thing that lets us bound blow up. So this first term, okay, so if MI is the amount of actually used user allocated storage in the heap on thread I, HI is the storage owned by heap I. In general, horde promises to maintain this invariant for all heaps I, that we're bounding by wasting at most half the memory in that heap and upper bounding it with some function of the superblock size. And we're going to do that by augmenting our free function, where X is owned by thread I, to say we're going to put X back in the heap. And then if we fall below this threshold, this invariant we're trying to maintain, we're going to move a superblock that's at least half empty from heap I to the global heap. So we're going to push ourselves back below this threshold by yielding memory from that thread local heap to the global heap to be potentially reused somewhere else. And that's going to be the key thing. We don't have time to unpack this in detail, but that's going to be the key thing that guarantees that we keep nice bounded blow up. And I encourage you to read this on your own, but the basic intuition is hopefully relatively straightforward. Okay. There's also a few other interesting allocators. We have a reading on something developed in Charles's group, Professor Licenson's group, called supermalloc from a few years ago. There's a very popular parallel allocator that's something you may wind up using a lot in practice today, called jemalloc. You should definitely check out. It applies a bunch of different optimizations, sort of builds on ideas from Horde and then does some more. And I just want to wrap up and show that both the complexity and performance and scalability of these different allocators can actually vary quite widely. So there's a lot of diversity in the field of real parallel allocators. So that's it for now. Sorry for running a second over time. Thanks everybody, and we'll hang around for a bit to chat.